Okay, so in this tutorial, we are going to continue with the numerical methods lectures, right? So this is going to be the lecture 6. We are going to talk about the numerical integrations. Numerical integrations are, sorry, okay. So numerical integration is also called the numerical quadrature, something like this, quadrature, right? And then they are essential for calculating the or estimating the area under a particular curve or the definite integral. So when we talk of the definite integral, we are simply talking about the area under the curve. Okay. So let's say you pick a function, right? Let's just pick some hypothetical function like this. The function looks something like this, right? If we want to find the if we want to integrate this function from probably this point, so let's say from x so to about maybe x5. If you want to integrate this function, what you are simply doing is that you are trying to find the area under this graph, right? So that's simply what integration is. So with numerical integration, we are not able to know probably the exact function it is. Maybe we just have points of the function. So we don't really have, okay, let's say this one is y equals x squared, then we can simply integrate this. But for functions that we don't know what the function really is, but we have points. So let's say we have points of where the function is, then we can say, okay, with these points, let's find a way of estimating the area under those graphs. Yes, so that's simply all what numerical integration is about. So let's discuss about some of the types of numerical integrations. You have the rectangular rule, right? But then we didn't do this in class. We have the trapezoid rule. It has long-standing history. You can check that out later. And we have the Simpson's rules. So the Simpsons rules, we have the 1/3 rule and then the 3/8 rule. We'll get to these ones in time. So let's start with the first one and talk about the trapezoidal rule or trapezium rule. It's similar to what you did in high school. So with trapezium rule, let's say we have a trapezium, right? We know that with a trapezium, two of the sides are parallel to each other, and then no matter what lines these are that connect them, whether they look like this or whatever they look like, you can estimate the area of a trapezium simply using this formula. So you say half of the height, that's how far apart the two parallel lines are from each other, multiplying the sum of the length of the parallel sides, right? So this simply gives you the area of a trapezium. So let's say we had a trapezium that has here to be 12 centimeters and then maybe here to be 3 centimeters. Then we have a separation of say 4 centimeters. Then we'll have our area of this trapezium to be half into bracket. Um, so we can say the height to be 4. So 4 on 3, and then you sum the sides. So that'll be 12 plus 3. Then that will give us like 215, right? So that gives us 30 cubic centimeter, right? So sorry, square centimeter. So with this 30 square centimeter, that will simply be the area of this. Let's see how this really applies to a graph. Okay, so let's say you have a graph like this. So let's say you have a graph like this. um, we don't really know the function of this graph. So just assumably you have a point here on the x-axis. So let me label this x and y, right? Sorry. So if this is the x-axis and then that is the y-axis, we can locate 2 points on the graph. So say A and B, and then with these A and B, each of them has like they have a separation. We can call this the h. So the distance here will be the h. So if we want to find the area of this graph, right, the area this graph is covering in this range, then we can simply say that, okay, we can estimate that to be a trapezium. And if we do that, you can simply see that we'll be off by this factor. Okay, so this will be the difference in the original area, because if we find here, so let's say this was what we brought. So let's say here, after using this formula, we have like something like 30 square centimeter. Then this will be the area of this section, but then we'll lose this part. But then that's not the concern, because numerical integration is simply about estimating, right? So this would be a margin of error. That is fine. you can reduce the margin of error if you reduce. So let's say, let me pick another portion that has not been properly damaged. So let's say we want to find from B to C. Okay, then we divide this into small sections, like smaller sections. Then we'll find that the trapeziums we will draw will not have like, so if you draw a trapezium, it will be almost like the curve, right? So you won't have so much deviation from that. Yeah, so you can add up these areas. So you simply do a summation of this area, so this area plus that, and then that will give you the total area under this graph in this range. So that's simply everything about the trapezoid arrow. So let's go pick a real example and then solve. So like I said, if you want to find the total area, you do a summation. So let's pick the formula from, I don't know if he'll give the formulas in the exam room, but if he doesn't, you can simply keep it in your mind. It's simpler, like it's just similar to this. Okay, so over here, let me try to explain something before we get to the formula itself. When we spoke about here in the previous this one, like over here, you would know that from here to here will actually be called some f of a, right, or a y, and then here will be some f of b. So that's the same thing we are going to do. So when you see the f of x or f of xi, it's actually a corresponding value of the function, right, at a point. So let's get to that. Okay, so over here we have, so you can simply keep this formula in your mind. It's just like the other one. So you say the area equals the height multiplying the first. So the first is the f of x naught, obviously, plus the last, right? Or you can say f of sk, it doesn't matter, all divided by 2, and then you add up every other, like every other factor, right, from k equals 1 to n, right, to n, and then you have that of the function. So over here, so that means that you add the first plus the last, you divide them by 2, and you add any other thing else inside the bracket. Then after that you multiply everything by the height. Okay, so let's pick some example we have here and then solve it. Let me write that down. Okay, so let's just assume that we're able to capture the motion of an object, right, a particular object, and then we recorded the time against the velocity of it. So we find that at 0 seconds the velocity was 0 because it was stationary, and then at 3 seconds the velocity was probably 14. Let's calculate in meters per second. Okay, so it was 40 meters per second. Now if you try to plot this, you would clearly see that it's not a straight line. It will look like something else, right? So 1 against 10, 1.2 against 12, to look some way. So you want to find the area under this graph. So what would be the area under a velocity time graph, right? So that's just the whole idea. So you are integrating velocity against time. Then what are you looking at? Once you integrate velocity against time, you simply be looking at probably a distance. Okay, and if you differentiate velocity against time, you'll be looking at an acceleration. So that's just what it is. So let's use what we mentioned. So to find the area under this graph, we take h. H is simply the distance between each of the x values. So here we find that, sorry, this is 2.0, right, this 2.0. Okay, so we find that these x values are equally spaced by a unit of 1.0. So we can say so let me call this TD, total distance. So if I say total distance, then that will be the height. So the height, I mentioned that that's the difference, so that will be 1 multiplying the first, so don't forget the formula, the first value, which is 0, plus the last value, which is 14. So these two divided by 2, right? I got this. And then now we continuously add anything else. So we add the otherwise. So we have 10 plus 12, right? So now let's compute this. This is 1, so it won't have much of an effect. So 14 divided by 2, that gives you 7, right? So 7 plus Then we have our 10 plus a 12, that gives us 29. So this tells us that the distance covered, right, by the body in this velocity time profile is 29 meters, right? So this is how it translates in real life. Let me pick another example, then we solve again. Okay, so this is just some random data. So let's say we have some particular function. So at x, a corresponding f of x or a y is 2.1 in that order. Okay, we'll use this particular example to evaluate the difference between the Simpson's rules, like that's the 1/3, and then the 3/8, and then against the trapezoid rule, and see what the differences are. So over here, let's do the same thing we said we'd do. So we want to find we don't know what this one is, we don't know what it's representing, so we can just say the integral of f of x, right, dx, right? So we are doing an approximation, so we use this. That's the height, so the height to be, so just refer to the formula height. So the height to be the difference here. So you have to always have a constant difference between your x values, else this formula will not work. So you have 0.5 plus the first and the last. So first is this, last is that. So we have 2.1 plus 2.8 all on 2, and then this one plus any other term. So we have 0.2 plus 0.4, which gives us 6.6. Then so we can say 6.6 plus 2.8, right? Then let's compute this. So the integral of f of x dx is approximately, okay, so if you punch this into the calculator, we have 0.5, and that's right. So let me just enter an equal sign. We have this, so this gives us 5.925. so you put down your answer, that would be 5.925. We don't know the unit, we don't know if it has a unit at all, so we just leave it. So that means that the integral of, or so let's say the definite integral of f(x) of this function is approximately 5.925, in that range, right? So that's just all about the trapezoidal rule. So let's now move to the Simpson's rules and then see how they compare. And you can find other examples and then with some different data and then work it out and see what you get. Okay, so let's move to the Simpson's rules. So the Simpson's rules, like there are some set of two. We're just studying two actually. We have 1/3 rule and then the 3/8 rule. They were invented by someone we call Thomas Simpson. So it's just like his name that's on it. And then what you find is that the 1/3 rule was, should I say, the first method for estimating the integral of a function, right? And then later the 3/8 rule was also published for more accuracy, like when you have functions that have like fast turning points, so it will be difficult estimating the integrals at those points. So that was the essence of the 3/8 rule. So that's why we have two rules we are studying. Now with the Simpson's rules, it's just basically the same thing. You have a formula, and then 1/3 rule works for, so we have even terms, right? So we're working with even terms, like even numbers and multiplications. But then let's check out what the formula is. Just try to keep in your mind. If it doesn't give it, then you'd have to refer to your mind for it, right? So this is going to be the formula we're going to use for the Simpson's 1/3 rule. Okay, so you have the h, that's the same difference we've been working with, by 3, so you divide it by 3. Now what you do is that you add the first and last, you don't divide now, plus 4 times all odd terms plus 2 times all even terms. So that's quite simple. So let's try and bring that out again. So we say the integral of the function with respect to x dx will give us our height. Okay, you can just call it height, so some difference, right? That will be the first one, or f of k, depending on how you're starting from, to the last one, f of n, so something like this. And then you now add 4 times all odd, right, plus 2 times all even. Now when we see an odd term, all terms are, let's say the first term will be an odd term, but then in this case, let's say the odd terms are the 3rd, the 5th, the 7th, in that order. The even term will be the 2nd, the 4th, the 6th, in that order, right? So let's pick an example, and then the example we are going to work with will be the example we used for the other example um, for the prior one. That was the trapezoidal rule. So let's just write that down. Let me write this example down. Okay, so let's pick this example. So we have a particular function 1.0 gives us that in that order. So with this data, it's just like the one we used earlier. It's the same thing actually. So we'll finish and compare the values we had. So over here, what we are going. Okay, so I've better illustrated the question so that you can see it clearly. So here we have our f of x, our x naught, x1 in that order. So this one becomes our first term, our last term, our odd term, this and odd term. Okay, so if you have to do the substitutions, you have your h on 3, that's 0.513 plus 2.1 plus 2.7 plus 4 times your odd terms, which is 0.2 and then 2.8, and then you add your final even term, which is just 1 in this case. So over here, when you do the computation, you should be getting something like this. So that would be like 5.933. Take note that with the first one we did with the trapezoidal row, you had something like 5.925, and then this one you have 5.933. They are quite similar, right? They are quite close. So this is for the Simpson's one-third rule. So let me just reiterate it. So you have an integral of a function x dx to be approximately equal to h on 3 times first term, so that will be f of x naught, plus your last term, and then plus 4 times all odd, so 4 odd, and then 2 times all even, right? So don't mix up the odd and even. So this is just the part for the Simpson's one-third rule. So let's move to the Simpson's 1/8 rule. Okay, so this was everything we did. So now to the Simpson's 1/8 rule. So like I mentioned earlier, the Simpson's 1/8 rule is better at estimating the area of curves that have sharp edges, right? So for a curve that moves like, so let's say we have let me just try and draw a hypothetical graph, like some particular graph somewhere. Okay, now if you have a graph that looks like this with this sharp edge, and then you are probably to find the area, so you might have to draw a trapezium. Sorry for that. Alright, so let's say we want to draw from A to B, and then you do something like this. See that you'll be off a very large portion of the graph, right? And this is really bad with accuracy. So yeah, so the Simpson's rule somehow is able to better estimate this graph. Like if you divide into more compartments, right? So let's say if you divide this into more compartments, you would have a better approximation of the total area or the total integral than other methods. So Simpson's 1/8 rule. Let's go to the formula. So with this one, so just like the first one, so the integral from some point, it's a definite integral, so we'll have limit of some function dx will be 3/8. That's why we call it the 3/8 rule. So 3/8 times the height, and then we multiply by the first term, last term, plus some recurrent this one. So that's 332, 332. So let's just reiterate that 332, 332. Now what this 332 means is that, let's say you finish with your let's say your 3/8 into bracket, so your first plus your last. Now whatever follows will look like this. So 3 times f of x1 plus 3 times f of x2 plus 2 times f of x3 plus 3 times f of x4 plus 3 times f of x5 plus 2 times f of x6. Now you get what I mean. So that's just like 332, 332. Okay, so that's just like a I don't know, it's a convention, it works anyway. So yeah, so let's just pick an example like the one we had initially and then see how we go about it. So let me just put down the data again, then you see. So we have some x, f of x, this example is actually in the slide, so you can pick it or find other examples that are similar and then try to estimate the differential and see how like you get it right. Yeah, so something like this. So let's use the Simpsons 3/8 rule to solve it. So we'll have a integral. It's a definite integral. Sorry with the first one. So it's a definite integral. It's like I left out the limit. So this is approximately equal to 3 on 8 times the h, which is the separation between each of them, which is 0.5. Then we multiply by the first term. We multiply will be the first term, so that will be 2.1 plus the last term 2.7, and we start at ratio. So here you have 3, 3, 2. You see it ends there. If we had more terms, it will just continue 3, 3, 2, 3, 3, 2. So here you can just always write it on top if you forget 3, 3, 2. So you have 3 times 3.2 plus 3 times 3.4 plus 2 times 2.8, right? So this is what we have. You can punch this into your calculator and see what you get. Okay, so if you punch this into your calculator, you should be getting something like this. And in decimal, we have 5.6625. Yeah. So this is an approximation of the different integral of the function we have. So yeah. So now let's do some small comparison between the three methods we've actually worked with so far. So comparison. So here we work with the trapezoidal rule, right? And then what we had for the same question was 5.925 for the Simpsons 1/3 rule. So it says Simpsons 1/3 rule, right? We had 5.933, and then for the Simpsons 3/8 rule, right, we had 5.6625. Now the question is, how do you know which of these is the most accurate? Like if I'm solving and then I probably have to use any of these, which one should I go for? Realize that these two values are closer. Does that mean these two methods are more accurate? Now that's not what we are saying. So what we can do to find out which one is more accurate, right, would be that we have these curves, right? We have this data, so we can plot this data on a graph, right, and use some computational tool to find or maybe we can even use these like finding the formula of a curve, right? So we can find the formula of the curve that best describes this and then integrate that curve, see the area we get from these 2 points, from 1.0 to 3.0, see the value we get, and then we compare to these three values. Then we can make conclusions on which one is the most accurate. So you can't say that okay, these two values are closer, so the 1/3 and the trapezoidal rule are most accurate. So that was just an addition. So that's basically everything we did in the numerical integration. So trapezoidal rule, Simpsons 1/3, and Simpsons 3/8. So once again, your trapezoidal rule, you just have to here. So here, this is the formula again. Just take one more time. So you have to add the first two, divide by 2, and then add the rest. With the Simpsons 1/3 rule, you deal with the odd even. So 4 times odd, 2 times even. You divide the height by 3 and add these two. And then the 3/8 rule, you have that. Right. So that's basically all for the lecture 6.